Physics 251, Video Explainer 3, Problem 65. A typical laboratory centrifuge rotates at 4,000 RPM. Test tubes have to be placed into a centrifuge very carefully because of the very large accelerations. Part A. What is the acceleration at the end of a test tube that is 10 centimeters from the axis of rotation? And Part B. For comparison, what is the magnitude of the acceleration a test tube would experience if dropped from a height of 1.0 meters and stopped in a 1.0 millisecond long encounter with a hardwood floor? So, to solve for part A, we will use this acceleration function, where A is equal to our acceleration, our R will be our distance, and W will be the angular speed. So, to solve for the acceleration of the test tube, we need to convert our angular speed and our distance into compatible units. And so, to do this, we will take 4,000 RPM and multiply it by 2 pi radians divided by our 1 RPM, and this will give our answer, or this will give us our angular speed in radians, and then because we need in radians per second, we will then multiply that by 1 meter divided by 60 seconds, and this gives us 418.9 radians per second. To solve or to convert our distance, we just need to go from centimeters to meters, and so to do this, we just take 10 centimeters times 1 meter divided by 100 centimeters, and this gives us 0.10 meters. Now that we have converted our angular speed and distance into compatible units, we can plug it into our acceleration function, and when we do this, we get the acceleration is equal to 0.10 meters times 418.9 radians per second squared, and this equals 17,547.72, or 1.75 times 10 to the 4th meters per second squared. For part B, we are solving for the magnitude of the acceleration of a test tube if it were dropped from 1 meter. And so because we don't have a time interval, we will use this velocity equation or function where v is our velocity, v naught is our initial velocity, ay is equal to acceleration, yf is the final vector displacement of the test tube, and yi will represent the initial vector displacement of the test tube. One important note for this equation, or for this problem, is that because the test tube is being dropped, the acceleration will be equal to negative gravity. We also know that the initial velocity will be equal to 0, as well as the final vector displacement. So we plug in our knowns into the velocity function, and when we do this, we get velocity squared minus 0 is equal to 2 times the negative 9.8 meters per second squared times 0 minus 1.0 meters. We will then simplify and take the square root of velocity to find that velocity is equal to 4.43 meters per second. We will then take this velocity and plug it into our acceleration function here for this v. The final velocity will be 0 because the test tube will be on the ground, and then we divide that by time. When we plug in our knowns to the acceleration function, we get 0 minus 4.43 meters per second divided by our 1.0 millisecond, and then to convert that into just seconds, we will multiply it by 10 to the negative 3 seconds divided by 1 millisecond. And when we do this, we get negative 4,430, or negative 4.43 times 10 to the 3 meters per second squared, giving us a magnitude of rounded 4.4 times 10 to the 3 meters per second squared. And this will be the magnitude of the acceleration of the test tube.